All right, let's do some examples from section 3.2, which is to take derivatives of exponential and logarithmic functions. So in section 3.1, you kind of played with exponentials and logarithmic functions a little bit because, maybe you haven't seen that in a while, so that was kind of review. And then if you look at the lecture notes for the class, I kind of derive a few of the rules for taking the derivative of an exponential and logarithmic function. So you can refer to those notes to see the rules. These will just be additional examples of the rules. So let me just recap the rules here. Hang on. All right, so if we have a function that is your basic exponential like e to the power of x, then its derivative, y prime, is e to the power of x. So the exponential e to the power of x is its own derivative. If we take another base as an exponential, so for example, b to the power of x, where b is not equal to e, then the derivative is similar. It's going to be b to the power of x, but then I have to multiply by the natural log of b. All right, so if it's any base other than the number e, I must multiply by the natural log of b. All right, for the logarithmic functions, I'll draw a little line here. If, again, I have a function y equals the natural log of x, then y prime is 1 over x. And again, the derivation of that is in the course notes, so take a look at that. And if you have a log function that is any base but e, like base b here, then its derivative will be similar. It'll be 1 over x multiplied by 1 over the natural log of b. So another way to write that would be 1 over the product x times the natural log of b. So, these are your rules for exponentials here on the left side of the screen. Here are your rules for logarithmic functions and taking the derivative. Okay, so we can practice that if in this first example we have a function f of x equals 5 times e to the x plus 3x plus 1. We know that f prime of x will be, remember we drag the coefficient along, so it's 5 multiplied by the derivative of e to the x, which is just e to the x, plus the derivative of 3x, which is 3, plus the derivative of 1, which is 0. So we see the derivative here, 5 times e to the x plus 3. In the next example, we have a function which is, has a logarithmic term. So we have f of x equals negative 2 times the natural log of x plus x squared minus 4. So we can say f prime of x will be, again, this coefficient negative 2 kind of gets dragged along. So it'll be negative 2 multiplied by the derivative of the natural log of x, which is 1 over x, plus the derivative of x squared, which is just 2x, minus the derivative of 4, which is 0. So I can write this if I want as negative 2 over x plus 2x. All right, in the next example, we'll take the derivative of the function 5x minus the natural log of x to the power of 5. Keep in mind that there's a property of logarithms that says this thing can be written as 5x minus 5 times the natural log of x. So whenever you have an exponent as the argument of a log function, that exponent can be written in front. So then the derivative of this will be the derivative of 5x, which is 5, minus, and again, I'll drag this coefficient of 5 along, so 5 multiplied by the derivative of natural log x, which is 1 over x. So this is just 5 minus 5 over x. Okay. All right, on to another example, which is a little bit of an application kind of. It says a student claims that the line tangent to the graph of the function f of x equals e to the x at x equals 3 passes through the point 2, 0. is she correct? And will the tangent at x equals 4 pass through the point 3, 0? So keep in mind that if f of x here is e to the x, then f prime of x is e to the x, right? The slope of the tangent here at 3, so, if I want to, I can find the slope of the tangent at 3 and then the equation of the tangent at x equals 3. And then check to see if this point 2, 0 is on that, it satisfies that equation. All right, so I'm going to evaluate f prime at 3, and I get e to the power of 3. So this is the slope of the tangent at x equals 3. All right, the equation of the tangent, remember, tangent is a line, so it satisfies this guy, mx plus b, and I already know that the slope is going to be e cubed. I know the value of x is 3, so I could plug that in. And I know that if x is 3, then the y that goes along with that has to satisfy this original function. So, f of 3 is e to the power of 3, right? So I have this, and that's my y value. So I know x is 3, I know y is e to the power of 3, and I know the slope is e to the power of 3. Those are the 3 pieces of information now that I can plug into the equation formula, or my line, I guess, form here. So this is going to be e to the power of 3 equals the slope, which is e to the power of 3 multiplied by x plus b. And now I can solve for b by subtracting 3 e to the power of 3 from both sides. All right, so I have e to the power of 3 minus 3 e to the power of 3 equals b. And this is just negative 2 e to the power of 3. All right, so my tangent line is of the form y equals e cubed x minus 2 e to the power of 3. And then the question is, does that line pass through the point 2, 0? Meaning if I plug in x equals 2 and y equals 0 into this guy, is the equation satisfied? So if I do that, I get 0 equals e cubed times 2 minus 2e cubed. And this just looks like 2e cubed minus 2e cubed, which is a 0. So the point 2, 0 does satisfy. So let's just say 2, 0 satisfies the equation of the tangent line, which is this guy. And therefore, it passes through that point. So to answer the second part of the question, I won't do it because it's the exact same process. You would repeat this process, but you would evaluate the tangent at x equals 4 to find the slope. You would find your point that the function contains at x equals 4, plug that in to find the equation of the tangent line, and then just see if the point 3, 0 satisfies that equation. All right, a couple more examples of just some simple derivatives. So in question 31, and I've mentioned before that this is from the previous version of the book, so maybe the numbers won't be the same in your textbook now, but the problems are similar. The derivative of the log base 2 of x, remember the derivative of the natural log of x is 1 over x. If we take the log some other base, it's going to be 1 over x times the natural log of whatever that base is, so times the natural log of 2. So this is all in the denominator of the derivative. And then similarly here, to find the derivative of an exponential, 3 to the power of x. So remember, it is its own derivative. Y prime is 3 to the power of x, but if your base is something other than e, you have to multiply by the natural log of the base. So times the natural log of 3. All right, and then the last question is an application. It says an experiment was set up to find the relationship between weight and systolic blood pressure in children. Using hospital records for 5,000 children, the experimentals found that the systolic blood pressure was given by, and you have this function, P of x equals 17.5 times the quantity 1 plus the natural log of x. We're given a domain on that function. It says P of x is measured in millimeters of mercury, x is measured in pounds. What's the rate of change of blood pressure with respect to the weight at a 40-pound weight level and then at a 90-pound weight level? So what is the rate of change in this case? That means, we want to find the derivative P prime of x, and then we want to evaluate that derivative at 40 pounds, and we want to evaluate that derivative in the second part at 90 pounds. I won't do that second part. Okay, we'll just interpret this 40-pound deal. All right, so keep in mind here that P of x is, I can distribute the 17.5. So I'm going to distribute the 17.5 in. So it'll be 17.5 times 1 plus 17.5 multiplied by the natural log of x. So that's my P of x. My P prime of x will be the derivative of 17.5, which is 0, plus, I'll drag my coefficient along, 17.5 multiplied by the derivative of the natural log of x, so times 1 over x. All right, so P prime of 40 would be the answer to the question, what is the rate of change of blood pressure at a weight level of 40 pounds? So I'm answering that part of the question. So that's just going to be 17.5 over 40, which is about 0.44 millimeters per pound. And, we can interpret this by saying, at the 40-pound weight level, blood pressure, remember P prime is giving you a rate of change of blood pressure. So we would say would increase at a rate of 0.44 millimeters per pound of weight gain. Okay, so again, P prime gives us the rate of change of P with respect to X.